Good morning. Today I would first like to recap what we did about master equations. As you remember, master equations are the time evolution equations for discrete state space Markov processes. The equation is a linear equation with a matrix Q. We call it the Q matrix. And what we did last time is we studied the properties of this Q matrix because it informs us about the approach to the steady state and the nature of the steady state. One important property of the Q matrix is that the row sum is 0, which is due to the conservation of probability. And then we looked at these Q matrices in a way that illustrates best how they approach equilibrium and how the states are connected to each other, which is a representation in terms of graphs. These graphs can have different types of nodes. As we learned, there is one class of nodes which is shown here on the left. These are nodes where every state is connected with everyone in all directions, so you can go from any state to any state as you like. This is an irreducible system. Once you're there, you stay there, and each state is recurrent. It comes up again and again and again. We learned about other types of nodes or states in such a stochastic system, which are transient states. If you take away the yellow arrow, there are also some kind of irreducible set. But if you add this yellow arrow, there is probability flow that goes out from these transient states and they lose, ultimately either towards a set of irreducible states or another set of irreducible states, or they can go to a special class of states which we call an absorbing state, because once you're in the single state, there is no way to actually get out. What we learned also is that in the case of a fully irreducible system, the steady state for a finite system is unique, and all the probabilities are strictly positive. That follows from a theorem in mathematics. Then we learned that there is a special class of processes. And they are by far not all interesting problems, by far not. The interesting problems are those that are not reversible. But if the process is reversible, that means the forward path and the backward path are equally likely, then you can show that there's detailed balance. And that means if you just pick a pair of states, so let's pick that one here, then for all of those pairs that you can pick, the flow from one side to the other and the flow from the other side back to the original side, they balance each other. Okay? So the current, which is the probability times the rate from I to j, is the current from j to I. Okay, today what we're going to do is we'll study some consequences of the detailed balance property, so a consequence of reversibility. And then we also study what does it mean that you deviate from detailed balance, and that will lead us to entropy production. And finally, I show you a neat application of detailed balance system, namely the Markov chain Monte Carlo, which is basically the numerical algorithm to solve problems in statistical physics. All right. Are there still questions about last time? If not, I'll start. So what we start with is we ask ourselves, how is the approach to equilibrium for systems that show detailed balance? All right. So this means we need to study the properties of that differential equation, so how it approaches the steady state. We know it's unique, right? But we need to have something about the properties of this matrix to know how the approach actually happens to the steady state. So in general, if you take a Q matrix, this Q matrix is not symmetric, and because it's not symmetric, you cannot easily diagonalize it. That's a problem in these systems, but it's also the beauty of those systems, because it means dynamics in general is very, very rich and interesting. So in the case that you have detailed balance, what I'm going to show you is that you can actually define a complementary matrix, which I define as follows, and there's no sum convention now here. I take my original Q matrix and multiply each of the elements Mn with the square root of the steady state, which I know to exist. Okay? There's no sum convention here. It's really multiplying each of the matrix elements with the probability densities, the square roots of them, and here to the minus 1/2 and here to the plus 1/2. Okay, that's a definition. And now let's see what are the properties of this matrix. And I'm going to show that this is a symmetric matrix. And once I've shown that, because this is a similarity transformation, I know that I can also solve the original problem in terms of the solution of the new problem. So let's go through the calculation. Here we have the off-diagonal elements of the Q matrix. That's the only thing I need to look at. So these off-diagonal elements, by definition, are given as I just wrote it. Pn to the half. Okay, and now let me rewrite this. Let me write this as Pm to the minus 1/2, transition rates, Pn to the minus 1/2. Just a very trivial rewriting. And I do this because I want to use the detailed balance condition. So this object that we have here, if you just look on the lower part of this board, you'll see you can use the detailed balance condition for that. So we can rewrite this as a Pm to the minus 1/2, and then I'll have here the inverse omega Nm Pm Pn to the minus 1/2. So here I use detailed balance. And now you just need to combine things again. You need to combine the Pm to the minus 1/2 with the Pm. So you get Pm to the plus 1/2. And you then reorder the factors of the probability distribution P. And you see this is just the inverse of the original term. So this is W of Nm, right? So we have shown detailed balance implies that this new matrix Q tilde is symmetric. Well, once you know it's symmetric, you know it has an eigenbasis. And this eigenbasis needs to have orthogonal eigenvalues, eigenvectors, and real eigenvalues. Okay? You also know from the theorem that I showed you that the eigenvalues are actually all strictly negative up to 1. One eigenvalue is 0, and the others need to be negative because they're now real. So that means I can diagonalize such that I have the eigenfunctions and the eigenvalues I write as minus lambda because I know that lambda equals 0 for the steady state, and else the lambdas are strictly positive, as I know from the Frobenius theorem, right? So that means this is very standard. You relax to a steady state here, and the relaxation to the steady state is purely exponential. And there's a gap between the lowest eigenvalue, which is 0, and the next eigenvalue that's positive. And this gap determines how fast the ultimate approach to the equilibrium is, because that's the slowest time scale that you have in the system. All right, now as we have that, we can then find a diagonal basis also for the original problem. So the spectral decomposition that we have, which is the diagonal of all these different eigenvalues, a certain number of them corresponding to the size of the matrix that we study. And this is found, as usual, by a transformation with a orthogonal matrix that I write like so. It's S n k tilde to the minus 1 q k l tilde s tilde lm. And the matrix that we have here is one that is a orthogonal matrix. Okay? That's a standard spectral decomposition for symmetric matrices. This is actually the same decomposition for my original matrix, and this is shown simply by writing things out. So let's start from this expression that we have here and just write the definition of q tilde. So this becomes sum over k and l, s tilde to the minus 1, nk, pk to the minus a half. So I'm inserting the definition of the q tilde matrix, pl to the plus a half, s tilde lm. Okay, and now I redefine the objects that we have here on the two sides of the Q matrix. I call them just S. And then you see what we gain is a transformation of the original matrix Q into diagonal form. Right. There's a subtle point here. The matrices, the matrices that we have here, the S tilde, they are orthogonal matrices because that's what you have when you diagonalize a symmetric matrix. The S here, they are not, right? Because now you have this definition that this is S coming from S tilde. So the matrix S is not necessarily a orthogonal matrix. Good. Finally, and this is now rather trivial, once you have the eigenvalues and eigenvectors of the transform problem, you also have an eigenvalue and eigenvector for the original problem. The eigenvalues stay the same, and the new eigenvectors, they are related to the ones of the tilde problem by a rescaling of the corresponding entries. So it's the same factor of square root of the probability distribution function that relates the two eigenfunctions. Okay, so that's great. Now we do have a solution. We know the eigenvalues. We know the eigenvectors. And that means for any initial condition, we can construct the probability density, probability, sorry, here, which is then a sum over all the eigenvalues with some coefficients C lambda that I have to choose such that I obey the initial condition that I want. Then I do have here the eigenfunctions and e to the minus lambda t. Okay. That's a very strong result now because it says that the relaxation of our system towards the steady state is a purely exponential relaxation. There's no oscillations, there's no complex eigenvalues. These are just all real eigenvalues. And that means the relaxation to equilibrium is not really something that's particularly interesting in a way that you have complex phenomena. It's a very simple relaxational process. Okay. Questions? Okay, so here if you go back to this state where you have an irreducible system, you also have a unique steady state. The probabilities are strictly positive as well, but we don't have a statement like for reversible processes. The approach to the steady state and the nature of the steady state can be much more complex and much richer. In particular, the eigenvalues, as you know, they don't have to be real, they can be complex. So you have all kinds of oscillatory processes that can happen in a more general case. And if you look into a high-dimensional problem with many species in space and in time, this can give rise to very rich phenomena. All right. Now, let me give you another important property of detail balance. And this is the Kolmogorov loop criterion. It states the following. If you do have a irreducible Markov process with a discrete state space, which is also finite, then reversible which we already know is equivalent to a detail balance condition, is equivalent to the following, that the transition rates for a process that runs in a circle, so let me draw a cartoon of that. You have here state 1, 2, 3, 4, 5, 6, and you have here a process that runs in one way or the other way as well. Okay. And there can be many other states, right? I'm just taking from the system that I study one of those loops of states. Then the statement is if you take any of those loops in your irreducible representation of the stochastic dynamics, then the forward transition rates from 1 to 2 all the way back to 1 is the same as the rates in the opposite direction. So from 1 to 2, W2 to 3, etc., closing the loop at n is the same as I take all the rates in the reversed direction. Okay. So why is this an interesting property? If you look at detail balance, if you want to check detail balance, what do you have to do? You have to actually know the steady state distribution and calculate it. And once you have it, you can check whether the product with the corresponding transition rates gives you the detail balance condition. It's very inconvenient because sometimes it's super hard to actually calculate the steady state distribution. Here, in this Kolmogorov loop criterion, you don't have to know the steady state distribution. All you have to check is whether for all the loops that you have in the system, the forward and the backward product of rates is the same. The proof of that I will not give you in the lecture. This is in my notes. And it's actually quite instructive to look through that. The forward direction, so showing that from detail balance you have the loop criterion is trivial. You just write it out and then cancel factors. The backward direction of the proof is a little more involved. All right. Questions? Okay, what I would like to do with you is actually to discuss the consequences of this kind of loop criterion and reversibility and irreversibility in a chapter now which talks about irreversibility and entropy production. So if you look at what we just had, irreversibility means there's no detail balance. Irreversibility also means that this loop criterion is not fulfilled. So the forward rates and the backward rates are not the same. So that means there's fluxes in the network. So no detail balance. You have fluxes in the network of states. And you would like to know what does that mean for the system? How could I characterize the system more in depth? So let's draw, and I did that before, a graph where I'm picking a time window that starts at 0, and I call this t0, and it ends at some time t, which I call tn plus 1, and I dissect my time into different time points, t1, t2, up to tn, and finally at tn plus 1. And we will look at trajectories of those processes, and we want to know then how we should characterize these trajectories. So let's say I'm starting out here at time equals 0 at some initial state n0, and the time points t1, t2, etc. are the time points where I have the transition to a new state. So here I hop to a new state I call N1, and this continues. And then finally here at time Tn, I jump to a state Nn, and I remain there until the final time, which is capital T. Okay? Let me introduce some more notation, as I did before. I want to name these intervals. These are time intervals tau 0, tau 1, etc. They are the time intervals of residence in a certain state. So tau 0 is the residence time in state N0. Tau 1 is the residence time in state N1. And I do have the corresponding exit rates for these states. So this is the sum over all states which are not the state K, and I'm transitioning out from that state K into the state L. And remember, this we called the exit rate in various discussions, including the discussion of the Gillespie algorithm and the discussion of also the proof of detailed balance. So now let's assign probabilities to the trajectories. So let me call gamma the forward trajectory. It just means I'm at state 0. And this is now my shorthand for the state N0. I transition at time T1. So after some time T0, I transition to state 1. And I do so in a successive manner until at time Tn, I arrive at state N. And I want to know what is the probability of this forward trajectory. So what's P of gamma? And that's very simple, right? We had this in the Gillespie algorithm. It's the probability that I start in state 0, which is P0. Then I have to transition, I have to wait for a certain time tau 1 before I make the transition. So that is then e to the minus alpha 0 tau 0. After I have waited this time tau 0, the next event happens. I transition from my state 0 into state 1. Then, well, I wait for a time interval tau 1. I transition from 1 to 2. And this whole game continues until finally I would transition from my state n minus 1 to the state n. And then I still have to wait and not exit from that state for this time interval tau n until I arrive at the final time t. Right, that's the forward probability. What is the backward path? Let's call this gamma bar. That's the backward trajectory. And that's now obviously in the other direction. You go from n to n minus 1 until you go back to 0. And you just take the same time points, just in the reverse order. That means I'm transitioning here at time Tn, and here the final transition is at time T1. So let's write down what the probability of this reverse path gamma bar is. Now I have to start at state n. The probability for that is Pn. Then I remain in this state for time, residence time tau n. Then I transition from n to n minus 1. And this whole thing continues until I do the transition from 1 to 0. And then I wait there patiently until time t equal 0 for the residence time tau naught. Okay, now you look at this expression and you ask yourself, what is the ratio of the forward path divided by the backward path? Okay, so you have all these transition rates, you have all the different probabilities, and you have all these exponential factors that correspond to the waiting time distribution for the various events. You should note that all the factors that come from the waiting time distribution are identical. They cancel out. So all that remains really in this expression is the probability of the initial state, the probability of the final state, and then I have in the numerator, I have the transition from 0 to 1, from 1 to 2, until the final state n. And I have to divide by the opposite. Okay, so I can write it like so now. This is from 1 to 0, from 2 to 1, and this is from n to n minus 1. So just reverse the arrows in the direction of how the states are going through. So why is this an interesting quantity? It's an interesting quantity because it quantifies to what degree the probabilities in the forward and the backward direction are actually different. Okay, so it is a measure of how irreversible my process is. And that's just that motivates the definition that I call now the entropy production along a path. I call this delta S for a certain path. I'll define this as the logarithm of the ratio of the forward path probability to the backward path probability. So let me now wipe the board. Okay, now let's rewrite this in a form which will help us understand this maybe even more. So let's write the delta S for a path such that I separate here the parts that come from the initial and final state probabilities and the rates. And since there's a logarithm, that's quite natural to do. That's the logarithm of the initial state and the final state. And that is then here the sum running from k equal to 1 through n. And that's then the logarithm of all the ratios between transition rates from k minus 1 to k. And I'm now writing this in this matrix notation again, and the backward from k to k minus 1. So it's a sum, as you see, of probabilities. And then here the second term is the sum of the rates in forward, the log of the rates in the forward and the backward direction. We call this here the entropy production of the system. and we call that here the entropy production of the environment. It's not clear here why I call the system an environment, because I don't do thermodynamics. This is a purely a picture in terms of stochastic trajectories. And if you would like to know why there's a system and environment, well, we would need to do a bit more of stochastic thermodynamics, but let's just leave it at this and take this as the term that depends only on the steady state distribution, which if this were to be some kind of statistical mechanics, this would be given by the Boltzmann factors characterizing the system. Here, that's transition rates, and for transition rates, you need to somehow plug into the energy environment of the system to make those transitions, and that's why this is called the environment contribution. And if you do thermodynamics, then you could actually relate those rates to thermodynamic potentials, but we don't go there. So let's just leave it at this and take those two terms as defining properties of my stochastic trajectory. And now I want to know a quantity which is a limit in the time going to infinity. I want to know what's the average of the production of entropy in my system. And for that, I need to do an average over time of these entropy production terms that we calculated and take the time to infinity. Okay. Now, if you look at that, what about this term? That term is a steady state, so it doesn't depend on time. P naught and Pn, they're both finite, different from 0, and they're bound between 0 and 1. So this is a bounded function, and that means if I divide by time and take any kind of average, this object will just be 0. What's non-zero in this limit is that second term, and here we can do a counting argument. So let's look at the term for the environment for a given path gamma. Here I'm now summing over all the different pairs of bonds that I have in my system, so all states ij. And Nij is the number of transitions that I do have in time t between the states I and j. And here I have the log of ij, comma j, or just ij divided by wji. Okay? That's the same expression as above. And now, what is Nij? Nij are the transitions between the states I and j. They happen with a flux given by Pj w j to I. And they happen so constantly in time. That's the constant rate or constant flux that you have of transitioning between the two states. So if you wait for time t, this will be proportional to time t as well. Okay, now that you have that, we can actually look at the average of this, delta S environment average, as a function of gamma. The t cancels, and I can easily take the limit because there's no limit to take anymore anyway. So this is then sum over all states ij, p j w ij logarithm of w ij divided by w ji. Okay, so that's the average of the entropy production in the way I defined it over a long period of time. You can rewrite this a bit, and I'll show this to you, I guess, after the break, but let me give you the final expressions before the break. There's two ways you can rewrite this. You can rewrite this as sum ij, pj, w, ij, log of p, j, w, ij divided by pi, w, ji. The difference now is that I have this equivalent to an expression where I can add here the pj and pi's. You will see how this works. And you can also write this as sum over ij, pj, w, ij minus pi, w, ji, logarithm of pj, wij divided by pi, wji. Okay, let's just look at this term, the first one. What do you see? When is this 0? This is 0 when the log is having argument 1. So it's 0 exactly when you have detailed balance. Okay? And that means now if you look at our derivation, it's very meaningful to look at the log ratio between forward and backward path because the corresponding quantity averaged over a long period of time is a measure of how far you are from a reversible process. The quantity you see here is 0 if you have a reversible process, and it deviates from 0 if you don't. So this is a proper measure of one measure of a distance from a system from a reversible